size exclusion chromatography lets us separate proteins by size. We can use it to purify or analyze. So size exclusion chromatography is a technique that we can use to separate proteins by their sizes, and it has really important uses in the lab when we're purifying proteins, often as like a polishing step, as well as for testing if proteins can form stable complexes. So like, can they bind one another and form a stable complex, maybe even stable enough to figure out a structure of them. So today I am running some analytical size exclusion chromatography. So basically, chromatography is basically where we have these columns filled with these little resins, so these little beads, and they have different properties. And then we flow a mixture of proteins through there, and then the proteins are going to separate based on how they interact with the resin. And so we can put in different types of resin, like things that have charge to trap charged proteins, things that have specific groups that'll bind to like affinity tags and that sort of thing. So there are different types of columns, and the size exclusion, what's inside the column is kind of pretty boring. It's just like agarose or like dextrose or something, so it's just like sugar. But what it's doing is it's actually going to separate the proteins by size. And the boringness is actually really important because the proteins aren't going to interact with the resin. They're not going to be like sticking to the resin. Instead, they're just going to be traveling through and around the beads, because these beads are like, they have secret tunnels. And so they have these different size tunnels inside of them. And so the proteins are going to flow through the tunnels differently, because the really big proteins, they're not going to be able to get through those tiny tunnels. But the little proteins are going to have to go through all the tunnels. This means that the little proteins are actually going to travel farther. So they are going to come off last. When we say they come off, that we say they elute from the column. And so the little guys are actually going to come out last. And so this is kind of opposite of what you see with when you do like an SDS-PAGE gel. So there are a few differences between this and SDS-PAGE. So I've talked a lot about SDS-PAGE in the past, but basically that's where you have like a flat gel and you run proteins through them. And when you're doing that, you're actually like denaturing the protein first, and you're coating it with this negatively charged detergent, so like this artificial soap, and that's gonna make the proteins all like linear and negatively charged, and then you actually use an electric gradient to get them to move through the gel. And in that case, your gel, you can think of it as like this mesh that all of the proteins are kind of just like swimming through, and the longer the protein, the more tangled up it's going to be. That is not what happens in the size exclusion chromatography. So you still have a gel mesh, but your proteins are folded up. And so your proteins are in like their functional size, and they're not negatively charged. You're not moving them through based on charge. You're moving them through, but you're just like pumping liquid through these columns. So these are like FPLC, so fast performance liquid chromatography, or protein liquid chromatography. I can never remember which one it stands for. But basically they have these pumps, and they're going to move liquid through the columns. And so you might have done some sort of chromatography, or seen chromatography done with like gravity flow, which you typically do in the cold room, which I hate. But basically you just rely on gravity to drip the protein through the column. But when we use an FPLC machine, like an AKTA, so I'll tell you more about why in a minute, but I'm actually using this old AKTA Explorer, which I just learned how to use yesterday after, so I didn't learn how to use it until after I got my PhD, because I've just been using like the AKTA Pure, which is much simpler to use, more automated type of machine. But with this one, I'm using it for the analytical, because as I'll show you, I can hook it up so that I have less dilution between, so like the path between the injection and the column is smaller, so I don't like dilute my sample as much, which is important for analytical chromatography. But anyway, so you have your protein flowing through these beads. And you're using the pumps to flow them through, but you're not using any electricity or anything. I mean, you're using electricity to power the pumps, but you're not using like an electrical gradient to get the protein to move through the gel, the mesh or whatever, as you would before. So you're not separating them you're separating them based on their size or their shape and not their length. And it's opposite to how things flow in the gel mesh when you're doing like an SDS-PAGE. In that case, the longer things are going to get tangled up more. With the size exclusion chromatography, nothing is getting tangled up. Instead, things are separating based on how far they have to travel. The littler things are going to have to travel further because they're going to have to go through all of those little tiny columns. So you can think of it kind of like a car, and it's on a journey. Or your proteins are different cars, and they're on journeys through the column. And these beads are filled with different tunnels, like roads going through different tunnels. And if you're too big to go through the tunnel, then you don't have to go through the tunnel. And so you get to go around the tunnel, and you get to take a shortcut around the tunnel. Whereas the small guys, they can fit through the tunnels, so they have to go through all of these little paths. So the small guys are going to have to travel further. So this means they're going to have to travel a further distance to the fraction collector. So all the proteins are moving because they are not interacting with the resin. They're not interacting with the beads, because remember, these beads are super, super boring. They're just like sugar. So they're really boring. So they're not going to interact with the resin, or at least you hope they're not. So they're all moving at the same like linear speed, but they're traveling different distances. So the smaller proteins are going to have to travel a further distance through the column, and so they're not going to reach the detector until a later point. Whereas the big guys, they don't have to go through those tunnels. They don't have to go through the big tunnels. And some of them, like if they're too big, like if you just have like an aggregate or whatever, it's going to actually come out in what we call the void, which is like the bit of stuff that goes like all the way around, like doesn't go through any beads. It just goes around all the beads because it's too big to go through any of the tunnels. So that typically you'll see there's like a void volume in your column. And so basically, before you have like the real stuff coming out, you'll get the void, and so that's going to include like anything that was already in the column, so from like a past run or from your equilibrium, as well as like any aggregates, so like clumps of proteins and stuff that couldn't go through those tunnels, so they had to they went around all the beads and they just came right out, and so you don't want that to happen. But the bigger proteins, they're going to come out first, and the smaller ones are going to come out last, as well as like salts, free, like small DNA, RNA, that sort of thing. They're going to come out at the end. So you can use size exclusion chromatography in a couple of different ways. And so we have these different types of columns that I'll show you we can do these different ways. But basically there's two like main types. There's preparative size exclusion chromatography and analytical size exclusion chromatography. And we also call this gel filtration. So it's the same thing. So size exclusion, SEC, gel filtration, we use those terms interchangeably. And so with preparative, you're doing this when you're doing like a purification. So I've talked more about preparative in the past. And so with preparative, we're typically using, depending on how much you're purifying, you're typically using columns like these, which are like 24 mil column volume. So it's like 10/300, so 10 millimeter internal diameter and a 300 millimeter length. Now we could use like these big ones when we're doing like a higher prep, so we have more protein. And I think in some industry they have like ginormous ones, but I've seen bigger ones than that, but not like the super ginormous ones. But I'd be interested to see one of those. But basically the point with the preparative is when you're purifying your protein, and you can kind of use it as it's typically like the last step in a purification. So you typically start with like affinity chromatography, so you take advantage of something that's super specific about your protein, like maybe like a tag or something. And then you often cut that tag off, and so now you have to separate it based on its other like natural properties, and so you can separate it by things like charge, hydrophobicity, various types. And then the last step is typically the size exclusion chromatography, and where you're separating based on size, and you can do it as sort of like a polishing step. It's also really great for like buffer exchange, because basically because the buffer, so like your solution that your protein's in, so like your pH stabilized salt water that the protein's in, it's going to go through like everything. It has to go through like all the tiny little tunnels and stuff or whatever. So basically you pre-equilibrate the column. So basically you fill it totally with the buffer. And so typically you do like 1.5 to 2 column volumes worth of the buffer, and then you so now when you flow your protein through, it's going to come out with like the buffer that you put in before. The buffer's going to be traveling way slower than your protein because your protein is having to doesn't have to go through all of the tunnels, whereas the buffer is going through like all of the tunnels, so it's going to go slower. So this is why it's really important to pre-equilibrate your column. But it also means that you can use this for like buffer exchange, because the buffer that your protein came in with, it's going to be traveling slower than the protein that your protein came in with. And so your protein is going to get like desalted and stuff. It's going to get exchanged into that new buffer. So it can be really helpful, like faster than dialysis and stuff and other methods for doing like buffer exchange. So, but basically with the preparative, you're trying to like isolate your protein and like keep it. So you're collecting your fractions, and then you typically like concentrate it down to a higher concentration and then store it or do things with it and all sorts of fun stuff with your like, and really relax because you just finished a protein purification and you should celebrate, or at least once it's in the freezer. But anyway, so that's preparative size exclusion chromatography, and that's a time that I've mostly done, but there's also analytical size exclusion, and here is the point is to basically take 2 proteins, mix them together, and see if they're binding to each other in a stable complex. So this isn't, if you don't see, basically, it's not a yes, no, can these proteins interact? And it doesn't tell you about like how strong the interaction is, like in quantitative terms or anything. But basically, if it's stable enough to form a complex that it travels together through the column or whatever, that's often a good indication that, well, they bind well, and that you can maybe then isolate that complex and use it for structural biology things, like trying to do cryo-electron microscopy, cryo-EM of a structure. And so you can use this technique in order to try to like optimize, test if things bind to each other, and also to optimize the conditions of their binding on tiny little bits of your protein before you waste a ton of protein trying to do things like crystallography or cryo-EM or whatever on your complex. You want to make sure you have like the best shot possible. And then the other, like just seeing if the things will bind. And so it can be a really great tool. So like if you make a mutation, can it still form the complex and stuff? And so how is this working, right? So basically, if we go back to our car analogy, it's like if you had a truck, it's going to be bigger than a little car. And so it's going to travel slower. It's going to travel faster than a little car because it's not going to have to go through as many tunnels. But if that truck is like towing the little car, now you have an even bigger thing, so it's going to travel through even fewer tunnels, and so it's going to travel even faster, and it's going to come out first. So basically, you can take protein A, run it alone, protein B, run it alone, and then run them together and see if you see a shift in the elution volume. So basically the peaks, they're showing you like, so when the protein is coming off the column, it's going to go to a UV detector. And the UV detector is going to detect whether there's protein present, because proteins can absorb UV light. So you typically measure 280, and then we typically measure 260 if we're doing like, for like nucleic acid binding proteins and that sort of thing. So, but basically it's just a way to see when the protein is coming off of the column. And so like before it goes into like a fraction detector, or for analytical, we're not even like collecting these fractions because they're so tiny. So basically with this analytical column, the idea is that you're not trying to like isolate the thing that you're really not trying to isolate the thing that you are separating. You're just trying to look at it. So kind of in this way, it's similar to SDS-PAGE in that you're just trying to look at it and not like take it out. But with SDS-PAGE, remember, things are coming off in the opposite order, and you're denaturing the proteins first. There's something called native PAGE, which I'm hoping to try tomorrow, where you don't actually denature the proteins. And so then you can see if complexes are forming that way as well. But you're still going to have the opposite direction, where the bigger things are going to travel slower. But with the size exclusion chromatography, the bigger things are going to travel faster because they're not going to have to travel as far because they're not going to have to go through all those tunnels. But so with size exclusion, with the analytical, so this column, it's like the same length as the columns that I normally use for preparative, but it has like 10 times less volume. So it's a 3.2 times 300. And so the column volume is only about like 2.4 milliliters. But so you might think, oh, it's gonna run really fast, except you run it at a way slower rate. So we're running it at like 0.04 mils per minute. So it takes like an hour or so to have the run. But basically, so the reason why I'm using it on this kind of old school one, so this Explorer. So here's the injection port. So you actually inject it with a syringe, with this like small syringe, and then it's going straight from this injection into this tiny little loop, and this loop is just going to hold like 20 microliters worth. And so a microliter is 1,000th of a milliliter, so we're talking really small volumes. And then it's going to go straight, when you tell it to like change to inject, it's going to go straight onto the column from here and through the column into the detector. And so we can see, like, so normally we hook it up, we have like an air sensor above it, so we have a bunch of extra wiring. And the problem is, when you have that wiring, you're diluting your sample. And so we don't want to dilute our sample because we want to have as like crisp as peaks as possible. And also with analytical, it's really important that you're injecting like the same amounts. So typically, if we're doing like a preparative, we have like bigger loops, and we want to inject just like half the column or like half the volume or less into the loop because we want to save all of it. So because with the size exclusion, you're not sticking the things to the beads, the order that they arrive onto the column is going to matter. And if you were to, so the point is to keep, like, not give any proteins too much of a head start. The more you dilute it in the beginning, the more dilute your peak is going, the more broad your peak is going to be, because some of the proteins, even if they were at the same size, they will have arrived at the column beginning a little bit sooner. So by minimizing the volume that we're injecting and by minimizing the dilution, so keeping that tubing short, we can then minimize we can make our peaks as sharp as possible. And instead of just filling it part way, so we make sure that we get everything going through. So basically, when we're doing preparative, we only inject like half or less of the loop volume. But then we tell the computer to run through like a whole loop volume or even more. And so this way you're pushing everything out and onto the column, and you make sure that you get your entire sample. So if you had, that ensures that you get your entire sample into the loop, or run or whatever. And you don't, because you don't want to like push some of it through and then not have the rest like pushed through because you're then going on to whatever. But anyway, it doesn't, you get it all on. With analytical, you want to like overflow your loop. So basically, if you just overflow it, it's gonna go to like waste and stuff. And you tell it to inject, and then it's gonna go onto the column. It's gonna stay in the loop until you tell it to inject. So basically, you can put it in load mode. So like inject, you can put it in load mode, and then it's just like going into that loop. And then when you're ready to inject, you can put it into inject, and then it'll actually go from that loop and onto your column. But so you want to make sure that the loop is totally filled, and you want to make sure that it's filled, like you want to overfill it. So even though it's like a 20 microliter loop, we load like 30 microliters, and the excess will just like go to waste and stuff, and it's no big deal. But you want the loop to be totally full, and because that'll ensure that you have the exact same amount between your different runs and you're not diluting it. So if you think going back to like trying to compare the peaks when you have a like two proteins and you're running them alone and then together, in order to compare, you need to have make sure that you loaded the same amount of the protein each time. Another thing to note is that a big protein is not going to get shifted as much by a little protein as a little protein will get shifted by a big protein. So it's easier to look for like the disappearance of the small peak often as opposed to the movement of the bigger peak. But so yeah, so basically you want to like wash the loop out. So you like take the syringe and wash it. So like you have a little thing of buffer. You pull up the buffer 2 times wash it with the buffer, and then wash your loop while you're in the load mode. Do like a couple loop washes. So here you have to do this all manually. With like the pures and stuff, you can do things automatically when you're using like the bigger columns and stuff. But because I wanted to use this one which we have set up in this mode, it's all manual, so it's kind of scary, but it's okay. And so you wash the loop, then you load your sample, and then when you're ready, you move it to inject, let it run through, let it go through a couple volumes of what you added, and then you, in terms of like the volume that you added, and then you can take your syringe out and wash it and all that sort of stuff. So make sure you wash it because you don't want the syringes to get like all crunchy and gooey and stuck with stuff. And then you wait and you watch. So remember, the stuff in the beginning is going to be the void, and the stuff that comes like in the very beginning is going to be the void. So check with your like manual to see what the void volume is. And then after the void comes out, it'll be your stuff. And remember that the bigger stuff is going to come out earlier, the smaller stuff is going to come out later. So we also have this like, so we're really fortunate. So we're like a structural biology lab, and so we have 4 AKTAs. So we have 3 AKTA pures and the Explorer. And so this AKTA pure we actually have set up with like this thing called a micro kit that I've never actually used, but it's basically, it has all the tubing so that it has even less dilution than this guy, but you can like only then run the analytical size columns on it and stuff. So I'd never actually used the micro kit. We didn't get it that long ago. It's the same type of idea, except you can inject like directly onto the columns and stuff, I think. But yeah, I haven't tried that, but some other people in my lab have, especially when the people doing like cryo and trying to really optimize the reaction conditions. As to what's in the columns, so basically you can get these like analytical size columns and the different types of columns that you can get with like the big size columns. And so typically these columns are filled with some sort of cross-linked sugar. So you're probably familiar, if you're at this point in the video, you're still here, sticking with me, you're probably familiar with Agarose Gel Electrophoresis, which we use to like separate DNA in like a slab of gel. So with Agarose Gel Electrophoresis, so agarose is the sugar, and we can get it to like gelify by just like heating it up and then like cooling it down, and it'll just like mesh together and like, kind of like knitting yarn. So you're not actually like cross-linking, you're not making any sturdy bonds between them. You're just like knitting a scarf. But so agarose is really good for these DNA gels because of its boringness, because the DNA is not going to like, it's going to get tangled up, but it's not going to be like sticking to the agarose because this agarose is really boring. So we want boringness here too, and so we can tell agarose is good for that. But just like you wouldn't want your, like if you've ever run like an agarose gel, you know how like jelly they are, and how like if you heat it, it'll just like melt. So you don't want to heat these columns up, but basically you can see that the agarose isn't strong enough for something like this, where you're using pressure. Like the pumps are putting pressure on the column. So we set a pressure limit. So with these guys, it's like 1.5 something. I don't remember the units. But you have like pressure limits because you don't want to crush the beads that are in there. But in order to like let them handle the pressure of the liquid being pumped through them, you need to make it stronger than if you were trying to pump liquid through one of those agarose gels that you run your DNA through. And so this agarose is chemically cross-linked. So basically you put covalent bonds, so like strong bonds in between them using some like cross-linking agent. So this might remind you of like SDS-PAGE, where in that case where when we make the gels, we are cross-linking acrylamide or polyacrylamide chains with like a bis linker and stuff. And so more on that in the SDS-PAGE post. But with that, you're using polyacrylamide, and here we're using agarose. So this agarose can be good, but for making this really sturdy beads and stuff, but it's not always. So so I think Sephiros is the normal agarose, cross-linked agarose, and then there's Superose, which is so I think this one's Superose is Superose is like super cross-linked, so it's even sturdier. And then there's dextran, so a different sugar. So that sugar has like better separating properties when you make a gel out of it, but it's less sturdy. And so the type I usually use is Superdex, which is a combination of like cross-linked agarose, so like the Superose and the dextran, so you have like kind of the best of both worlds type of thing. But so different columns have different types of like resin inside of them, and they also have resin with different size tunnels. So some of them are better for separating really big things, some of them have better resolution for separating really small things, some of them are more like broad range. So you can think of these kind of like as using different percentages of SDS-PAGE gels to separate things. So you can choose different columns based on your different like the sizes of the proteins that you are trying to separate.